In this episode, we will talk about Bielik V3 Small Technical Report. We're going to be taking a really close look at the Bielik V3 series today. These are some interesting new generative text models, specifically tuned for the Polish language. And we've got the technical report right here. We'll be focusing on the two main models they talk about. One with 1.5 billion parameters and a slightly larger one at 4.5 billion.
That's right. And the fundamental idea behind Bielik V3 is actually quite significant. They're setting out to demonstrate that you don't necessarily need these absolutely enormous 100 billion plus parameter models to get top-tier performance, especially for a specific language like Polish.
Yeah, smaller can still be powerful if it's done smartly.
Exactly. These models, the Bielik ones, they're optimized, and the aim is to rival or maybe even beat much larger models, but using way less computational power. And that has huge implications for accessibility, for efficiency.
Absolutely. And it's not just about making them smaller, is it? It's about how they achieved it. The report points to some key innovations. One is a custom Polish tokenizer they developed called APT4. That's Algorithm Prompt Tuning version 4. And they also use something called an adaptive learning rate. Let's maybe start with that tokenizer, APT4. So a tokenizer, just to remind everyone, is that first step where the model breaks down text into smaller pieces, into tokens. The fact that they made a custom one for Polish suggests they really thought about the language itself.
Precisely. The efficiency of that first step, the tokenization, it's critical, especially, for these smaller models that are working under tighter resource constraints. A good tokenizer, one designed for Polish, can basically represent the same meaning using fewer tokens compared to a general, say, multilingual one.
Okay, fewer tokens means faster processing.
Exactly. Faster processing, you can handle longer chunks of text, and ultimately you get better performance out of the model without needing more computing power. And APT4 is an improvement on the earlier APT3, so they're clearly iterating and refining this.
And this wasn't trained on a small data set either. The report mentions a really substantial, carefully curated corpus, 292 billion tokens from 303 million documents.
Yeah, the scale is massive, and that word curated is key. The volume lets the model learn all the, statistical patterns, the nuances of Polish. But the curation, the quality control, that's vital for building a model that's actually robust and reliable, not just memorizing noise.
And it seems to have paid off. The report shows really impressive performance across a whole range of Polish language benchmarks. They mentioned the OpenPL LLM leaderboard, the complex Polish text understanding benchmark, CPTU, that's a mouthful, Polish EQ bench for emotional intelligence, and even a Polish medical leaderboard. So a really wide spread of tasks.
And what really jumps out is the claim about the 4.5 billion parameter model. It's reportedly competing with models that are 2, maybe even 3 times its size. That's a serious gain in efficiency. You're getting more bang for your computational buck, basically.
And the smaller 1.5 billion one?
That one's positioned as offering, really solid performance in a very compact package. Think mobile devices, embedded systems, places where resources are really tight. So it's a significant step forward for efficiency in Polish NLP.
Which brings us to the potential impact, especially for languages like Polish that are, less represented in the big AI resource pool. Developing these huge models costs a fortune, computationally and financially. That can be a barrier.
Absolutely.
So Bielik V3 seems to be tackling that head on, making high-quality AI more accessible for Polish-specific applications, even if they don't have massive budgets. So our mission today is really to unpack how they did this. What are the technical details behind this performance?
Exactly. What architectural choices, what training methods allowed them to get these results? Let's maybe dive into the model architecture first.
Okay. The report says both models, the 1.5B and the 4.5B, are based on the transformer architecture. No huge surprise there. That's kind of the standard backbone for these models now, right?
Right, it's the foundation. Transformers are just really good at handling those long-range dependencies in text, which you need for understanding and generating coherent language.
And Table 1 in the report gives the specifics. The 1.5B model has 32 layers, a model dimension of 1536, 12 attention heads. Context length is 192 tokens.
And then scaling up to the 4.5B model, you see the increases. It goes up to 60 layers, a bigger dimension of 2048, 16 attention heads. And look at the context length, 32,768 tokens. That's a big jump. It can handle much longer documents, keep track of context for longer.
Interesting, though, some things are the same. Both use 2 key value heads, head size of 128, vocab size of 32,000, and both use SwiGLU activation, we should unpack that, and rotary positional embeddings, ROP, with data set to 1 million.
Right. And attention bias and MLP bias are true for both. MLP is multi-layer perceptron.
The intermediate size in the feed-forward part also differs, 8960 versus 11,008.
So yeah, the extra capacity in the 4.5B model is mainly coming from more layers and, wider internal dimensions.
Okay, let's dig into some of those techniques. Self-attention with causal masks. That sounds fundamental.
It is. Self-attention is the core engine. It lets the model weigh the importance of different words when processing another word. The causal mask part is crucial for generation. It basically forces the model to only look at words that came before the current word it's trying to predict.
So it can't cheat by looking ahead.
Exactly. It maintains that autoregressive property, predicting the next word based only on the past words, essential for generating coherent text.
Okay, the report also mentions grouped query attention, GQA, says it reduces complexity and memory use. How does that work?
GQA is a more efficient version of the standard multi-head attention. In the standard version, every attention head has its own query, key, and value calculations. GQA cleverly reduces the number of key and value heads. Multiple query heads share the same keys and values.
Okay, so fewer calculations.
Fewer calculations, less memory needed. It's especially useful for those really long context lengths, like the 32K one in the 4.5B model. And often, the performance drop is minimal. You noted both Bielik models use just 2 key value heads, while the query heads scale up.
Makes sense. Efficiency again. Now, SwiGLU activation. You mentioned this better than the older RayLU rectified linear unit. Why?
Right. SwiGLU stands for Swish-Gated Linear Units. It's a bit more complex than RayLU. RayLU is simple. Positive input passes through, negative becomes 0. SwiGLU uses a gating mechanism. It multiplies the input after a linear transform by a gated version of the input using the swish function.
Gating, like opening or closing a valve for information flow.
Kind of, yeah. It gives the network more nuanced control over the information flow. This often leads to better learning, smoother training, and just, better overall model capability.
And rotary positional embeddings, ROPE, enhances understanding of relative positions and helps with longer sequences. Why relative position instead of just numbering the words?
So older methods often just added a vector based on the word's absolute position, like word #1, word #2, etc. ROPE is different. It applies a rotation to the query and key vectors in the attention mechanism. The amount of rotation depends on the relative distance between the tokens.
A rotation in that high-dimensional space.
Exactly. This has a couple of key advantages. First, it directly encodes relative order and distance, which is often more important linguistically than absolute position. Second, because it's relative, it tends to generalize better if you feed the model sequences longer than it saw during training. The relative relationships still hold. That theta parameter, the 1 million value, controls how fast these rotations happen, basically how sensitive it is to distance.
They also mention RMS norm root, means square-layer normalization for stability and speed, and pre-normalization. Seems like they really fine-tuned the training setup.
Absolutely. RMS norm is a slightly simplified, faster version of layer normalization, which helps stabilize training. And pre-normalization, putting the normalization before the attention and feed forward layers instead of after, that's been shown to help models converge faster and more reliably during training. Every little bit helps.
Okay, so we've got the transformer base, these advanced techniques, but the report says they didn't build these from absolute zero. They adapted them from Quen 2.5 models using depth upscaling. Figure 1 shows this.
Yeah, depth upscaling is basically a way to make an existing model deeper, add more layers. They started with the Quen 2.5, 1.5B, and 3B models. Figure 1 illustrates the process for scaling the 3B model up to the Bielik 4.5B. The Quen 3B had, I think, 36 layers. They essentially duplicated some of the outer layers. Figure 1 suggests a block of 8 layers is duplicated to reach the 60 layers of the Bielik 4.5B.
So they copied existing layers to make it deeper.
Kind of, yeah. It implies a similar process for the 1.5B model, too. But crucially, this wasn't the only change. They also swapped out the tokenizer for APT4 and then did extensive pre-training on their Polish data.
So it was a strategic move. Leverage a good existing model. Quen 2.5 performed well and had that permissive Apache 2.0 license increase its depth and then heavily adapt it for Polish.
Exactly. It's pragmatic. Why reinvent the wheel? They could focus their resources, their compute, on the Polish adaptation part, the tokenizer, the data.
Makes sense. Let's talk more about that tokenizer, APT4. Motivation was better efficiency for Polish. Table 2 compares it.
Right, Table 2 is interesting. It compares APT4 to APT3, Mistral V0.1, and the original Quen 2.5 tokenizer. They tested it on the Polish and English preambles of the Polish constitution. For Polish, APT4 produces 503 tokens, fewer than Mistral, slightly more than Quen 2.5 and APT3.
Okay, but token count isn't everything, right?
No. Look at characters per token, CPT. ABT4 gets 4.78 for Polish. That's much higher than Mistral's 2.40 or Quen's 2.87. Higher CPT generally means more efficient encoding. Each token carries more information.
And tokens per word, TPW.
APT4 has 1.62 TPW for Polish, again better than Mistral, 3.22, and Quen, 2.69, though slightly behind their own APT3, 1.48. So it seems APT4 hits a good balance for Polish.
And the difference with English is stark in the table. Quen's tokenizer, for instance, is much better on English than Polish, really highlights why a language-specific tokenizer matters.
Totally. Multilingual tokenizers have to compromise. A Polish-specific one like APT4 can be optimized for Polish grammar, subwords, morphology. The report also mentions they considered how APT4 handles numbers, punctuation, special characters. All those little details matter. And yeah, it's the successor to APT3, showing that iterative improvement.
So they have this new APT4 tokenizer. How do they get the pre-trained Quen models to actually use it?
Yeah.
The report mentions reinitializing the token embedding matrix. That sounds like a major change.
It is. The embedding matrix is like the model's internal dictionary, mapping each token to a vector representing its meaning. Change the tokens, you need new vectors. The old vectors from Quen's tokenizer don't mean anything for APT4's tokens, so they had to create new embeddings.
How do you do that without losing all the knowledge the Quen model already had?
Good question. They didn't just start randomly, although that's one option mentioned, random initialization, but it can be slow. They evaluated several smarter methods: frequency-based vocabulary transfer, linear interpolation, something called Wechsel, focus, which stands for fast overlapping token combinations, using SparseMax OFA one for all, and Raman. Quite the list.
Wow. What's the core idea behind those fancier methods?
Many try to leverage existing information, maybe use word frequencies or pre-trained embeddings from other models, like Wechsel, OFA, Raman do, to give the new APT4 token embeddings a better starting point than just random noise. The goal is to transfer some semantic knowledge, make the subsequent training faster and more effective.
And they landed on focus. Fast overlapping token combinations, using SparseMax. Sounds complex, but effective.
It seems so. Focus tries to build the new embedding for an APT4 token by finding similar tokens in the old Quen vocabulary and combining their existing embeddings. The sparse combinations part, using SparseMax, means it focuses on combining only the most relevant old tokens. It's a clever way to preserve prior knowledge while adapting to the new token set.
Okay, so tokenizer swapped, embeddings initialized with focus, then what? The report talks about duplicating outer layers, freezing most of the model, training on 56 billion tokens, then unfreezing everything. Why that multi-stage approach?
It's a strategic fine-tuning process. First, duplicate the outer layers again to add some capacity specifically for adaptation. Then freeze most of the original Quen weights, train only the new APT4 embeddings and those newly duplicated outer layers on a chunk of Polish data, the 56B tokens.
So a focused adaptation phase first.
Exactly. Let the model quickly learn the basics of Polish with the new tokenizer without messing up the deep general knowledge already stored in the frozen layers. Once it has that foundation, unfreeze everything and continue pre-training on the full Polish dataset. This allows the entire model to fine-tune and specialize for Polish nuances. It's resource efficient.
Got it. Okay, architecture and tokenizer covered. Let's move to the pre-training data itself. The main goal was boosting Polish proficiency, accuracy, and fluency. They built a new dataset using the SwiGLU project. What's SwiGLU?
SwiGLU is an open science initiative. They focus on creating large, high-quality datasets specifically for training language models with a real emphasis on Polish resources. It's a collaborative effort.
So they use SwiGLU resources, select the 294 million documents using metadata like topic and stylometric features, trying to get quality and diversity. Then rigorous cleaning and quality evaluation, which we'll get back to. And importantly, they excluded data where terms prohibited training use.
Yep. That ethical consideration is crucial. You can't just scrape everything. Respecting usage rights is fundamental for responsible AI.
The result was a Polish corpus of 237 billion tokens. But they didn't stop there. They added English text from the Slim Pajama dataset. Why English?
To mitigate catastrophic forgetting, That's when a model trained on task A forgets how to do task A after you train it intensely on task B.
Ah, so adding some English helps it remember the general language skills from the original Quen model while it's learning Polish.
Exactly. It helps retain broader understanding, maybe some transfer learning happens too, but it's a balance. You don't want the English data to overshadow the Polish learning. Slim Pajama is a good choice. It's large and clean.
Interestingly, they also threw their instruction data set into this pre-training mix. Why expose it to instructions so early?
It's kind of like priming the pump. Giving the model early exposure to the format of instructions and answers might help it grasp the concept of instruction following before the dedicated fine-tuning stage. It could make that later supervised fine-tuning more efficient.
So the final pre-training data set was massive. 292 billion tokens from 303 million documents, a mix of curated Polish, some English, and even those future instructions.
A very comprehensive mix.
Okay, back to that data cleanup and quality evaluation. They use heuristics for basic cleanup, removing junk, anonymizing data, fixing encoding, standard stuff. But the quality evaluation sounds much more involved. Manual annotation into high GH, medium, and low quality categories.
Yes, that manual labeling is key for creating a ground truth. Humans read and judged documents. This labeled set 44K training, 3K test, 1K validation docs was then used to train an automatic quality classifier.
And they even added synthetic data to these categories. Why create fake examples of good, medium, and bad text?
To really stress test the classifier, it's hard to find enough real-world examples of specific problems consistently. So they created synthetic high GH quality, like good markdown, medium with tense shifts, topic drift, and low quality examples. The low ones mimicked common LLM failures. Incoherence, factual errors, repetition, looping, hallucinations, bad machine translation, especially from distant languages like Chinese where errors are more obvious.
That's thorough, ensuring the classifier could spot a wide range of subtle issues, not just typos.
Exactly.
And they use more features for this classifier than before, 200 stylometric features in V3, up from 150 in V2.
Yeah.
What kinds of things do these features measure?
A whole spectrum. Lexical richness, like unique words, rare words to detect repetition. Diacritic and encoding checks for garbled text. Sentence structure analysis. Readability scores. They even use named entity recognition, NER, to check coherence. Do the names and places make sense together? Morphosyntactic diversity variety in grammar. And analyzing parts of speech distribution.
It's like creating a detailed fingerprint for text quality. They used a pipeline based on stylometrics, plus Unicode handling, and a dependency parser for grammar structure. And XGBoost was the best algorithm for the job.
Yes, XGBoost, a powerful gradient boosting method, gave them the best results. 95% accuracy on the validation set, 0.85 macro F1 score. It was very good at spotting HIGH, 0.97 F1, and low 0.97 F1 quality. The medium category was harder, lower recall, 0.51, which makes sense. Medium is inherently fuzzier.
Right, easier to spot great or terrible than just meh. So they used this classifier to filter the pre-training data.
Yep. They set thresholds, needed a probability of high GH 0.50 or probability of medium 0.80 to be included. Anything below that was out. They even shared the XGBoost hyperparameters, which is great for transparency. Figure 2 shows the confusion matrices visually.
Okay, quality sorted. They also built a category classifier to assign documents to one of 120 topics. Why?
Primarily for thematic diversity. They wanted to ensure their training data wasn't skewed towards just a few topics. By classifying documents, they could build a balanced data set.
How'd they build that one?
Trained on over 58,000 labeled Polish documents. Used a standard text classification pipeline. Count vectorizer for word counts, top 15K words. T-fetch transformer for weighting those words. And a linear support vector classifier, linear SVC, for the actual classification, with calibration for probabilities.
And it worked well.
Very well. 94.6% accuracy on the test set. F1 scores above 0.95. Table 7 shows the details, so it could reliably sort documents by topic. Table 8 and Figure 3 show the topic distribution.
So these two classifiers, quality and category, were crucial tools for crafting that high-quality, thematically diverse pre-training data set.
Absolutely. They laid the groundwork for the next stage, generating synthetic data for instruction tuning.
Right, let's get into that. The report describes a very structured process for this. First, generating high-quality QA instructions.
Yes, they took documents already flagged as high GH quality, PHIGH 0.9, and ensured they had a good mix of topics using their category classifier. Then, using controlled prompts, they had a model generate question-answer pairs based only on the content of those high-quality documents. Emphasis on factual coherence, clarity, Natural language.
So, generating reliable training examples from the best source material. What about this data recycling idea? Improving imperfect texts.
This was clever. They took medium quality documents where the classifier was confident it was medium, and also some borderline high GH quality ones, PHIGH, between zero point 0.5 and zero point 0.7. They fed these into their older Bielik V2.3 model to automatically fix things like spelling errors, formatting issues, minor OCR mistakes, trying not to change the core meaning.
Like an automated proofreader.
Kind of, yeah. Then, these recycled documents were reevaluated by the quality classifier. Only the ones that passed a stricter quality threshold after cleaning were added back into the main training corpus.
So, salvaging potentially useful data from texts that weren't perfect initially? A smart way to maximize their data pool.
Exactly. It's a two-pronged approach. Generate pristine new instructions from the best stuff, and carefully recycle and improve the good enough stuff. Shows a real focus on data utility.
Making the best possible training sets for both the foundational pre-training and the later instruction tuning.
Precisely.
Okay, pre-training done. Now, post-training. The focus here shifted to improving specific skills. Coding, math, logic, instruction following, first step. Supervised fine-tuning, SFT.
Right. SFT is where you train the model on examples of prompt and desired reply. You explicitly teach it how to respond to instructions.
They used a masked token strategy during SFT. What does that mean?
It means when they calculate the training loss, the error signal, they only calculate it on the reply part of the example. They mask out or ignore the tokens from the original user prompt and any control tokens.
So the model only gets rewarded or penalized for generating the correct answer, not for repeating the question.
Exactly. It focuses the learning on the generation task itself.
They also use an adaptive learning rate, ALR. Why adapt the learning rate here?
Because instruction response pairs can vary hugely in length. A short answer has fewer tokens than a long essay response. Without adjustment, the batches with longer sequences might dominate the training updates. ALR scales the learning rate based on the total tokens in the current batch compared to a reference batch size. The formula uses the square root of that ratio.
Okay, so it balances the influence of short and long examples for more stable training.
Precisely. And the data for SFT was an improved version of their Bielik V3 dataset over 19 million Polish instructions, 13 billion tokens. They cleaned it up, removed bad samples, regenerated some, added new ones using Bielik V2.3.
They list all the SFT hyperparameters too: Atom W optimizer, cosine learning rate decay, gradient clipping, mixed precision sample packing, 1.2 ABOX, 8K context length. Very detailed.
Yep, shows careful tuning.
After SFT came preference learning, trying to make the model's answers align better with what humans prefer. They tried DPOP or RPO, SIMPO.
These are all methods that use human preference data, typically pairs of responses where one is marked chosen and the other rejected to steer the model. The report says DPOP, direct preference optimization with penalty, worked best for them on Polish benchmarks.
What's the penalty part in DPOP? How does it improve on regular DPO?
DPOP adds an extra term to the DPO loss function. This penalty helps handle uncertainty or noise in the human preference labels. If the preference signal isn't super clear for a pair, the penalty discourages the model from making drastic changes based on that uncertain data point. It aims for more robust alignment.
Makes sense. And they boosted their preference dataset for this.
Big time. 126,000 Polish-only instructions. Broader categories, including function tool calling, more focus on reasoning and math, more conversational style. And they used a wider range of models, including Bielik V3, to generate the chosen rejected response pairs. Again, full hyperparameters listed for DPOP.
Okay, SFT, then preference learning with DPOP. The final post-training stage was reinforcement learning, specifically for the 4.5B model using GRPO.
Yes, Group Relative Policy Optimization, GRPO. This was aimed squarely at improving math problem solving. They used a curated dataset called RLVR, 12,000 Polish math problems with solutions they could verify automatically, selected from a pool of 100K.
And train this on a serious hardware setup.
An 8-back H100 GPU cluster at CipherNet using the VERL framework. This RL step is computationally heavy.
How does GRPO work? How's it different from something like PPO, proximal policy optimization?
GRPO is interesting. Unlike PPO, it doesn't rely on a separate critic network to estimate reward values. Instead, for a given math problem, GRPO generates multiple potential answers, a whole group of them. It gets a reward score for each answer, for example, based on whether the solution is correct. The key is how it calculates the advantage for each answer. It compares the reward of one answer to the average reward of the entire group generated for that same problem.
So it's learning based on which answers were better relative to the other attempts it made for that specific problem.
Exactly. It updates its policy to favor answers that outperform the group average. This relative comparison, without a separate critic, can be more stable and efficient for tasks like math, where you have a clear reward signal. The report details how they calculate the group means dimensional divergence term and the final objective function, including a KL divergence term to keep it from changing too drastically from the previous version.
Clever, a group-based learning approach. And finally, they mentioned model merging.
Yeah, linear merging. It's a simpler technique where you basically average the weights of two or more trained models. Sometimes the merged model inherits the strengths of his parents. They used it after SFT and RLHF stages, likely to try and squeeze out a bit more quality.
Right, okay. That covers the whole development process. Now, the proof is in the pudding, the evaluation. How did Bielik V3 actually perform? Let's start with the OpenPL LLM leaderboard.
This leaderboard tests various Polish NLP tasks, sentiment, NER, summarization, QA, etc., but not conversation. It uses zero-shot and five-shot evaluation. Scores are averaged and normalized against baselines. Importantly, they note PLM models are excluded because those were trained on the benchmark data, which isn't a fair comparison.
Right, so Bielik's results. Table 9 for base models, Table 10 for instruct.
The base Bielik 4.5 BV3 scores really well, beating some significantly larger Polish models. The 1.5B base holds its own in its size class, but the instruction-tuned versions, especially Bielik 4.5B v3.0 Instruct, show huge gains. The 4.5B Instruct model outperforms even larger models on this benchmark average, really highlights that parameter efficiency.
Okay, strong start. What about the Polish EQ bench, measuring emotional intelligence in Polish?
Table 11 has these results. Again, Bielik 4.5 BV 3.0 Instruct does impressively well for its size, beating several larger models. Even the 1.5B Instruct shows decent EQ understanding. The report notes nice efficient scaling here.
Then the complex Polish text understanding benchmarks, CPTUB, understanding implied meanings, tricky questions.
CPTUB has two parts: integers, sentiment, nuance, phraseology, and tricky questions, logic, ambiguity, humor. Table 12 shows the scores. Bielik 4.5B v3.0 Instruct again shows great parameter efficiency, performs on par with much larger models, especially on the implicatures and phraseology parts. The tricky questions part is hard for all models, Bielik included. That seems to be a general challenge for current LLMs. The 1.5B Instruct also does well for its size.
And the Polish medical leaderboard, using actual board exams.
Table 13. The results are quite strong here, especially relative to model size. Both 1.5B and 4.5B show good medical reasoning. The 4.5B gets remarkably close to their own much larger 11B model here, and the 1.5B even beats some larger models. It suggests good generalization to specialized domains, even without specific medical tuning.
Interesting. How about cultural knowledge, the Polish Linguistic and Cultural Competency Benchmark, PLCC?
This tests Polish history, geography, culture, art, grammar, vocab. Table 14 has the results. Again, good parameter efficiency and competitive scores. Maybe not quite reaching their larger V2 models on this specific benchmark, but still a very solid performance showing good cultural grounding for their size.
They also tested on English benchmarks, right? Open LLM leaderboard, mix of all, Berkeley function calling.
Yes. Tables 15 through 18 cover these. It gives a broader picture. Mix of all correlates well with human evils like chatbot arena, so it's a good general check. The function calling benchmark tests interaction with tools. Bielik models generally performed well, especially on function calling in the controlled tests. It shows they have solid foundational capabilities beyond just Polish.
So across the board, especially on Polish tasks, the takeaway seems to be remarkable performance for their size.
Absolutely. The consistent theme is exceptional parameter efficiency. They're getting a lot out of those 1.5 and 4.5 billion parameters thanks to those Polish-specific optimizations.
The report is candid about limitations too, though. Factual inaccuracies can happen.
Yep. Standard LLM caveat. They can still make things up, hallucinate.
And despite cleaning efforts, training on public data means potential for biased, offensive, or just plain wrong outputs still exists.
It's a critical point. Users need to be aware. These models are powerful tools, but not infallible or perfectly neutral. Ongoing research on safety and reliability is vital.
Okay, let's wrap this deep dive up. The Bielik V3 series, these 1.5B and 4.5B models, really make a strong case for parameter-efficient modeling, especially for a language like Polish.
Definitely. Those key innovations, the custom APT4 tokenizer, the adaptive learning rate, seem to have paid off handsomely. Achieving competitive results against models 2 or 3 times larger on so many Polish benchmarks is a significant achievement. It's huge for resource-constrained applications.
And it sets a new bar, really, for efficient Polish language models. It's genuinely exciting to see this kind of high-quality AI work happening for languages that aren't always in the spotlight.
And they're not stopping. Future work includes boosting reasoning, finding more efficiency gains, adding domain knowledge. It sounds like the Bielik project has a lot more to come.
So, as you, our listener, think about this: smaller, more efficient models achieving top-tier performance for Polish products. What does this signal more broadly? Could this be the start of a trend, making powerful AI truly accessible for many more languages around the world, languages that have been underserved so far? Could this help build a more diverse, more inclusive AI future? Something to mull over.